Hello, good afternoon, everyone. My name is Sebastiaan la Fleur. Also for the next presentation, the next couple of presentations, they're called lightning talks. They're going to be very focused presentations, so very short ones. And I have the honor of starting. It's going to fit in very nicely with the last talk, I think, I hope. I'm going to use the last presentation as a reference for a couple of points. So first off, the talk is going to be a short introduction about future-proof protocols for energy flexibility, and then specifically the future-proofness of them. A little bit about myself. I'm a newbie at Linux Foundation for Energy, so I thought I'd take a small couple of seconds to introduce myself. I'm a freelance software engineer. I have an IT architect background, and I'm going to show one of the energy flexibility protocols called S2 as well. Which I've worked at while I was employed at a Dutch research institute called TNO, as well as after I switched to freelancing. So first off, an energy flexibility protocol, what does that look like? So we have these assets or distributed energy resources, theirs. And we have an optimization engine. And we want to use this optimization engine, of course, to shift or use energy flexibility of these assets. And I've put a question mark in the middle because these components, they need to talk to each other. And as we saw in the last presentation, that means that you have to communicate with a lot of different types of hardware. So how cool could it be if we could standardize that? So that's the goal here, to gain a protocol that is future-proof, and that is a standardization of both controlling but also gathering information about these energy assets. Currently, there are two options that I personally know of. The first is called AEBUS, which originates from Germany. It's quite popular there. And the second one is called the S2 standard, which originates from the Netherlands. They're both EU-focused, and they have a very different design approach on this standardization. So the first one, AEBUS, it's actually a tiered protocol. So actually all of the bullets, they present one of the tiers inside of the protocol. The first one's called SHIP, which is an abstract protocol to gain trust between this optimization engine and the assets in some way and to ship some kind of binary data. So it's really about just connecting. The second tier is called SPINE, which is a generic data model, which allows the usage of specifying some type of optimization goal and or energy or information about an energy asset in a very generic way. And then lastly, we have something called use cases. So use cases can be something like limiting power consumption or production, monitoring a battery, or even optimization, self-optimization of self-consumption by using heat pump flexibility. So shifting the heat pump in some certain way to coincide more with, for instance, solar panels. Now these use cases, they are specified using SPINE and they are communicated over the wire using SHIP. So this is how these three tiers work together. Like I said, S2, another option, takes a different approach for standardization. So instead of using specific use cases that revolve around some type of optimization goal, the standard actually specifies device types. And these device types are very generic. I'm going to show a couple of examples. And they do not depend on the optimization goal like AEBUS does. So different design approach. These device types, a couple of examples here. It's an incomplete list. I put in three examples here. So the first one is called fill rate-based control, which is a name for an energy asset with some kind of energy buffer or storage, like an electrical battery, or also heating a house, because a house contains a lot of heat energy. You can use the current temperature as the state of charge. And then the protocol, the S2 standard, actually specifies status information on the actuators, on the current level of the storage, financial cost, required power, everything that you need in order to make a correct optimization using this type of asset. The second one is called power profile-based control. And this one has to do with assets that have any type of predefined execution plan, like a washing machine or a dryer. Or even a dishwasher. So usually white goods. And these assets, they actually define a number of programs usually. And you can actually shift between the programs, you can shift between different steps. And this asset type allows you to both express all these programs, but also give you a little bit of control about how to shift between the programs to shift energy or delay certain parts of your program. And finally, I've also added demand-driven based control here, which is a device type where some type of demand profile needs to be satisfied. Similarly to the earlier example of the heat pump, with full-rate-based control, you can also say, okay, instead of modeling the current temperature inside of the house, I actually just specify the heat demand as a profile and say, this is what I want the house to be heated by. And then with demand-driven based control, you can actually use it to model the asset where it can deliver this demand in different ways. Specifically, hybrid heat pumps fit very well here because you can either use gas or electricity to satisfy this heating demand. So it allows an optimization engine to switch between the two whenever necessary. As I have shown with the heat pump or hybrid heat pump example, you can actually use different device types to model the same asset, and it gives you different types of control. Now that we've seen these protocols, the question remains, how do we ensure that these are actually future-proof? Because if we don't make them future-proof, we're going to have another transition on our hands quite soon. And I'm going to zoom in into actually two different requirements, namely what happens if we introduce a new asset and what happens if we introduce a new optimization goal. So I have a table here with the two protocols as columns and some type of score that I've given it to give some feeling of what kind of, how well it scores basically on these requirements. And on the left, for each of the rows, we have a different requirement. So the first one, when we're talking about introducing a new asset with AEBIS, if it fits within an existing use case, it's perfect, but it probably won't fit inside an existing use case if it's asset specific. So the example of self-optimization with heat pumps, if you use a different type of heating asset inside of your home, you would need a different use case, and that requires an update to the protocol. With S2, however, we have generic device types, and usually we expect that new types of assets will actually fit within these device types. So if it fits inside of one of the existing device types, perfect, no update necessary. However, if more information is necessary, then also with S2, we actually require an update to the protocol. With the second row, we look at introducing a new optimization goal. And with AEBIS, because it's centered around optimization goals with the use cases, every single new use case would actually require a change to the protocol. With S2, there's no mention of optimization goals or constraints inside of the protocol whatsoever. So this one is actually a bit more future-proof in this specific regard, where if you want to optimize it in a different way, for instance, when a new market gets introduced, which in the Netherlands is an actual example, we are introducing a new market called GoPakstar, a new energy market. It would require a change on the EBUS side, but not on the S2 side. Finally, something that I've noted with both protocols, I haven't been able to find any requirements when it gets to updating these assets. So if, because of one of the other examples, one of the assets actually need to be updated, we are looking at a situation where the updates need to happen some kind of way outside of the protocol. The protocol doesn't help or facilitate this in any way. Now, as the last presentation said as well, having just an open standard is not enough. You also need to make sure that everything around it is open or in such a way possible that you don't rely on any proprietary steps. And I'm going to show you a small example about local versus cloud deployment. Because in the Netherlands, what we see happening is with these introductions of these protocols, is we see that manufacturers find it really difficult to include it inside of their devices. They have their own proprietary protocol probably already implemented that connects with their own data center. And yeah, they find it difficult to introduce these new types of protocols in their devices, is what we've been seeing. And what the solution to this they seem to do is They use their own proprietary protocol to communicate all the information from, for instance, a heat pump to their data center. And then from their manufacturer's data center, they actually supply all the information through one of these open standards. However, if you do this, the manufacturer becomes a point of failure. If they stop supporting your device, you run the risk of, as a customer, as a consumer who owns this heat pump, they run the risk of not having their asset actually be able to inform any type of organization or party about the energy flexibility. And also it monopolizes the communication to the asset, which basically means that the manufacturer chooses for you which other parties or energy management systems they support in order to submit the energy flexibility to. Which means that even though it's an open standard, it's still not really open. You cannot choose yourself. So to finalize, we looked at what an energy flexibility protocol is, where it fits inside of the puzzle. So it's between the energy management system, the optimization component, and the energy assets. We've seen two examples. We also looked at the future-proofness, and finally we also noted that it's actually not sufficient to just have an open standard. Everything around it needs to be open as well. Thank you so much for your attention. If there are any questions, bye. If there are any questions, feel free to reach out to me after the talk or perhaps by email. I also included a quick QR code to my LinkedIn and GitHub. And I also included a couple of resources about the S2 standard. Thank you so much.